For a period in the 1980s, I worked at a pretty large organization. They had 3 mainframe computers, a couple of mini computers, and at the beginning of the 1980s, no microcomputers. The mini computers were used for specialized purposes and were not really connected to the rest of the organization. So the mainframe computers were really at the heart of operations. To the best of my recollection, the 2 IBM mainframes were connected to one another, but they were not connected to the CDC mainframe. The manner in which people accessed these computers was via terminals. So from this computing center in the middle that housed the mainframes, we had cables running out to everywhere in the organization where the terminals were situated. And people could then sit in front of a terminal and access the mainframe computer. In such a situation, the network is pretty different from what we've discussed thus far. Most of the network exists between the mainframes and the terminals. In fact, in a couple of cases, it would consist of a single link that would run from the mainframe to the terminal. And the challenge then was to manage that link. How do you determine who can put information onto that link? It may be the mainframe or it may be the terminal. Now, given this balance, intelligent mainframe versus a dumb terminal, it would make sense to give control to the mainframe. So one would use what is known as a master-slave setup. The mainframe would act as the master, and the terminal would act as the slave. And the master could then either ask the terminal, do you have something that you want to send to me, something that the user has typed on the keyboard, and the terminal could then send it. And that operation is known as polling. The master could also select the terminal to say, I have some information that I want you to display on the screen so that the user can read it. And that process is indeed known as selection. So in a mainframe condition, we have a master-slave mechanism. The master either polls the secondary machine to ask it for information, or it selects the secondary machine to tell it that it's going to send information to it. In addition to these point-to-point links, it also made sense to have multi-point links. In the case of a multi-point link, the link would run from the mainframe to a couple of terminals. So all the terminals on this link would be connected to the end point of the link, and the mainframe, whenever it sent out something, had to say, I want to talk to terminal number 1 or terminal number 2, terminal number 3. All the terminals will be connected to this link, but only the one that is being addressed is the one that will respond. So the master could poll terminal 1, or it could select terminal 2, and so on. This introduces a notion of addressing, even though there is no routing involved. Of course, the link between the 2 mainframes posed a similar challenge. But in this case, it was harder to decide how to manage the link, because the 2 machines connected to the link were equals. They were both mainframe computers. Obviously, it's possible to still designate the one mainframe as the master and the other one as the slave, and then the master can ask the slave, so the one mainframe can ask the other mainframe, do you have something to send to me? And then the other mainframe can do it, or the master can select the other mainframe and say, I'm going to send you some information. But nothing can be initiated from this secondary mainframe. So the master-slave solution is not an ideal solution. And as the size of networks have increased and we are more and more linking computers to one another that are all intelligent in the sense of computing, it makes less and less sense to try and use a protocol such as a master-slave protocol. So something else is required. In this video, which is the first of 5, we will look at the data link layer, layer 2 in the protocol stack. What the data link layer does is it manages the link between two computers. Now, when I say two computers, I mean between possibly multiple computers that are connected to the same piece of wire. Scenario that we had with a multi-point link where the mainframe was on one end and the terminals were on the other end. However, in general, you can have multiple computers, multiple intelligent devices that are linked to a piece of cable or to some other transport mechanism that can physically transport the signal. So the question becomes a much harder question, how to manage this link, how to control this link when there are so many intelligent devices that are linked to it. Recall that the physical link is layer 1, the physical layer is layer 1, and what we will be doing on layer 2 is to facilitate the transmission of data via the physical medium, via layer 1. And layer 2 is the layer that will make this possible. What are the challenges of managing a link? In other words, what needs to be done so that a physical link can transport logical data across that physical link? Well, one of the first challenges we need to look at is that of data delineation. Data delineation refers to marking the start of a piece of data and the end of a piece of data. So it indicates the start of a packet or the end of a packet. And perhaps very fittingly, we tend to call packets on layer 2 frames. So what we are meaning by data delineation is how do you frame the data? How do you put it between two endpoints? I know delineation is sometimes a hard word for people to spell, so keep in mind that the core concept of delineation is the line. Where do you draw the line? At the beginning of a packet or of a frame and at the end of a packet or a frame. Also, if there are multiple fields in this frame, how do you draw the lines between the fields so that you can select the appropriate information? The second aspect is that of media access control. I'm going to abbreviate it with a rather well-known abbreviation for that. And the question that media access control poses is who is allowed to use the medium? Who is allowed to put access on to put data on the physical layer? Some people will also refer to the same function as contention control, because the various stations that are linked to this physical medium are, in a sense, fighting about access to it. And how do you resolve that problem? We'll see some rather interesting mechanisms that are used for this. Just as an example, the master-slave protocol that we mentioned in the introduction is an example of such contention control or media access control. So you've already seen one. We will encounter others as we go along. And then the third aspect that I want to discuss is that of error control. Error control occurs on the data link layer to ensure that data is transmitted correctly via the medium. So whatever goes down to level 1 should arrive at the other end without any changes. However, it's important to remember that error control does not only happen on layer 2. It also happens on all the other layers. If you think about SMTP, if a email message cannot be delivered, machine will typically keep on trying for perhaps 4 days before it will tell you that it could not deliver the message. Also, if you send an email message to a mailbox that doesn't exist, then that SMTP protocol will tell you that it couldn't deliver the message. With HTTP, we know the 404 error where content doesn't exist. We also know about a couple of errors, other errors that are exposed to us. On the presentation layer, you have error control. On the network layer, you have error control when a packet, for example, cannot be delivered, and so on. So for all layers, there is a notion of error control. And in a sense, I'm cheating a little by mentioning it here on layer 2 and then expecting you to think about error control on all 7 layers. But we're going to just discuss it in detail on layer 2. The type of error control that occurs on the data link layer, as we indicated a moment ago, is about the integrity of the data that will be transmitted via the physical medium. Has that data changed or not? The first possible error control mechanism that we can use is parity. I assume you are all familiar with parity. It's where you add another bit to your, let's say, 7 or 8 bits in a byte, and you can then either use odd or even parity, and the parity bit that you use is adjusted so that all the bits in your field happen to be even or happen to be odd, whatever you've decided it should be. You are probably also aware that parity is not a particularly good error control mechanism, because parity will not detect a sequence of errors that cancel one another out. For example, if you're using even parity and something happens so that you are transmitting a sequence of zeros, then the parity will also be 0 and you won't even see that problem that has occurred. So take note of it. It is a well-known technique, not particularly useful. The second technique that we have to mention is that of cyclic redundancy codes. Rather specialized field to find a good polynomial to use with cyclic redundancy code, and we won't go into the maths of how to find such a good polynomial at all. But this is a much better technique. It is commonly used in error control on networks. And then the final technique that we will consider here is the notion of Hamming codes. The difference between these techniques, the important difference for our purposes, is that CRC will enable you to detect quite a number of errors. If multiple bits are changed and so on, it will be detected. Hamming code is useful if errors need to be corrected. We again have the typical scenario. If you're using optical fiber, then you will hardly ever have a transmission error. And then just checking that nothing has happened using a CRC is good enough. Even on copper cable, that's probably good enough. There you expect a few more errors, but not much more. However, if you're using Wi-Fi, then all sorts of things will go wrong, and you expect a lot of errors. And those errors are very often caused by the number of radio signals that are in the air. So just retransmitting and retransmitting may actually worsen the condition. and therefore error correction becomes more of an issue, rather than just telling the sender, I got your message, but there is a mistake, it's not been received correctly. You can say, I got the message, let me just check, and if I can correct it, then I don't have to ask for it to be transmitted again. Let's look at one small aspect of cyclic redundancy codes. As I said, we're not going to go into the mathematics because we don't have time for that, but we can at least look at how cyclic redundancy codes are calculated. Cyclic redundancy codes are based on polynomial division. In general, if you think about a polynomial, it will probably be something of the form ax squared plus bx plus c. One way in which you can specify that entire polynomial without writing the polynomial out would be simply to provide the coefficients. So ABC tells you exactly what that polynomial is if you know the convention where the A's, the B's, and the C's are going to go. The polynomials that we will be using are binary polynomials, which means the A's and the B's and the C's, the coefficients, can only be ones or zeros. So you can specify an entire polynomial, binary polynomial, by writing down a value such as 101. That would be 1x squared plus no x plus 1. Previously we indicated already that we're not going to talk about the selection of good polynomials, but a typical polynomial that will be used for error control will probably be x to the power 32, so 32-degree polynomial. We're not going to use examples as long as that because we simply don't have space to do that. But the process is very simple. To illustrate this, suppose that the polynomial that we want to use happens to be represented by that 1101. Let's say we have some data value, and this is just a number that I'm writing down, and I want to protect it with this chosen polynomial. What I will do is I will do polynomial division, and I'm going to divide the 1101 into it. Now, in the end, I want to divide it, in a sense, into every bit, which means I also want to divide it into that final bit that I've got there just before the end point. Since I'm going to use 4 bits for my division, when I divide it into that final bit, I'm going to need 3 additional bits to subtract a 4-bit polynomial from it. So because there are 4 digits in or 4 bits in my polynomial, I have to extend the value that I want to protect by 3 bits. Eventually, I'm going to replace those 3 bits by the CRC. This division uses what is known as 1's complement. Don't confuse it with 2's complement that you've encountered elsewhere in binary arithmetic. So 1's complement is very simple in the sense that 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 0 is 0, and 0 minus 1 is 1. So we never ever borrow anything. It's basically an XOR that we are performing. If we look at the first possible position where we can divide our polynomial into the value to be protected, it will use those 4 bits. And when we look at this initial bit, we can say that this is going to divide into that value once. However, our quotient that we're getting here is not important. If I make mistakes there, I don't care about it. What I care about is what I get in these lower 3 bits eventually. So I've set this divides into it once, so I have to subtract it. And I'm doing that with 1's complement, so 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is 1, and this uppermost 1 minus 1 will be 0. I've dropped a bit, and that's exactly what I wanted to have done. So what I can do next is I can bring down that 0, and I'm asking whether I can divide my polynomial into that number. And the only thing that I look up to make that decision is the leading bit of the number that I'm dealing with, and that's a 1, so the answer is yes, I can. And then because I can, I'm subtracting 1, 1, 0, 1 from that, again using 1's complement. 0 minus 1 is 1, 0 minus 0 is 0, 1 minus 1 is 0, and the leading bit by definition is going to disappear. What I do next is I bring down the next bit, and again I have a 4-bit quantity. And when I ask the question, can I divide my polynomial into that value, the answer is no. I'm just again looking at this leading bit, and that's a 0, so I can't do that. So I'm going to subtract 0 from this, and subtracting 0 from this will give me the answer or the result there, 0, 1, 1. The initial bit will disappear, getting rid of 1 bit at a time, and I will bring down my next 0. Now again, when I look at this polynomial and ask, can I divide it into that number, that leading bit is again 0, so the answer is yet again 0, and I'm subtracting 0 from this value that I'm working with, and this happens to be leave me with a 1, 1, 0, again getting rid of that leading 1 or leading 0, that leading bit, and now I can bring down the 1 that is next in line. So my answer is determined yet again by my leading bit, and I can say 1. Yes, I am able to subtract 1, 1, 0, 1, and going to subtract the 1, 1, 0, 1. Since I'm at the end of the screen, I'm going to continue here to the right. It will be a bit hard to follow, but hopefully it will still make sense. So the rightmost bit position that I'm using here is a 1 minus 1. That gives me a 0. Then just to the left of that, I have a 0 minus 0. So that gives me a 0. And then just to the left of that, I have a 1 minus 1. So that gives me a 0. And then at the extreme leftmost position, I have a 1 minus 1. That's the initial bit, the leading bit that I want to get rid of. So I managed to do that. So now I have to bring down the next bit, which is a 1. Looking at this value that I'm dealing with right now, I have a 0 in that position. So the answer, whether I can subtract it, is no, I cannot. So subtracting 0 from that gives me 0, 0, 1. I am killing that bit in the process. Bringing down the next bit is the first of these 3 zeros that we added at the end, and asking whether we can subtract our polynomial from this value. Again, looking at the leading bit tells us no, we cannot. which means we're subtracting 0. That leaves us with 0, 1, 0, and this initial bit has been removed in the process. To continue this process, we now bring down the second of those 3 bits and ask the question, can we subtract our polynomial? And the answer yet again by looking at the leading bit is no, we cannot. So that gives us a difference there of 1, 0, 0. The leading bit is cancelled out in the process, and we can now bring down the final bit in the whole process. So we couldn't subtract it. Looking at the final value, we have a 1, so the answer is yes, we can subtract it. So 1, 1, 0, 1 to be subtracted from that value will give us a 1, a 0, and a 1. And we don't have any further bits to bring down, so that is the remainder that we are stuck with. That is the CRC that we calculated out of this entire process. So the value that I will actually transmit is 10110101. It's the original data that I started out with. That is what I want to transmit. And then in the place of the 3 bits that I added initially, the 3 zeros, I now add the CRC. And this value is now protected. It is protected in the sense that when I do this division calculation using this value, I will get a remainder of 0. So if we repeat this entire process, but put the CRC, the 101 in there, we are guaranteed a value of 0. Doing that at the receiving end, doing this division again, will inform the recipient that this value is indeed correct, that it has not changed. Let's quickly do that and verify the process. Let's check whether we indeed get a 0 as a remainder. What I have here is the data I wanted to transmit. We've added the CRC, and we're going to divide using the same polynomial. Since the quotient doesn't play a role at all, I'm not even going to try and calculate it while I do this. I'm simply going to do the arithmetic at the bottom. So great, we got a 0 as a remainder, which means our calculation was correct. The data was indeed transferred correctly. I'll leave it as an exercise for you to go and change one of the bits, any bit in that calculation, or rather in the original data, or even in the CRC, and then do this division and see whether you end up with 0. You should not. If you do get a 0 for incorrect data, then something is clearly wrong. This brings us to the end of our discussion of CRCs. We will leave a discussion of Hamming code for the next video.
Music you're listening to is completely electric.